Agora é a apresentação do professor Dr. Tom Eskridge, né? Ele é professor associado no Departamento de Ciência de Computação e Engenharia de Software da Flórida Institute of Technology, Florida Tech. A formação dele é PhD em Ciência da Computação, especialização em Inteligência Artificial e Sistemas Inteligentes. Ele atua nas áreas de Inteligência Artificial, Sistemas Multiagentes, Representação do Conhecimento. Ele foi um dos colaboradores no desenvolvimento do CIAIM, Engenharia de Software, Aprendizado de Máquinas, Sistemas Especialistas. Ele tem várias publicações na área de interação homem-computador e desenvolve sistemas baseados em conhecimento e presta consultorias em projetos de inteligência artificial e engenharia de software. So, thank you, Professor Eskridge. Now you can start your presentation. Thank you very much.
All right, thank you, everyone. I mean, it's a real pleasure to be here. I think I might be the last talk because I think I'm not in archival science, but it's interesting the overlaps that I'm seeing in the work that I've been doing, that I've done in the past, in terms of things like CMAP tools for knowledge elicitation and knowledge capture, looking at ontologies for provenance and for metadata creation. And so this has been a really interesting evening so far. And I guess where I'd like to position this talk is we've been hearing a lot about the uses of AI. And one of the things that we've been really working on in my group is this notion of how people should interact with that AI. So if I'm a user of this AI tool, what is the best way for me to interact with that so that we get better performance overall, better performance for me, and better performance as an overall process. So, you know, to think about, we're going to start out with teams. And so some of the people that have been working on this team, we have Dr. Mizrahi from our philosophy department, who has done a lot of work with us on ethics and ethical reasoning. Dr. Marco Cavallo, who's actually from Brasilia, is our director of both our Harris Institute for Assured Information Lab and the Florida Tech Research Institute. And Kazuhiko Momose and Troy Weeks are two PhD students who we graduated, who have been continuing to do work with us in this area. And we were lucky enough to have Claudio here for almost a year, for a number of months. And he was greatly involved with especially with my students. And so I really appreciated our discussions and the help that he gave to our students. These are our graduate team. We have our PhDs across the top there. They're all doing work in this notion of how people are interacting with AI. And we have one master's student over there on the left, Lakitha, and one undergraduate student who's doing some really interesting work on anthropomorphic AI and what the benefits and drawbacks of anthropomorphizing AI are. And so it's a good team, and we've been chasing work in a lot of interesting ways, we think. So one of the things that we've known and you've heard about through the talks that we've done so far is you know, AI is the disruptive technology, and it's disrupting work everywhere we go. So if we look at what the economic impact of that is going to be, just from the AI uses alone, we're looking at around, you know, $2.6 to $4.4 trillion worth of work. But if you look at the overall impact with the increments that you get from worker efficiencies who are using that AI, that doubles. And so I think it's a valuable research area to be looking at of how that productivity, how are we going to get that doubling of economic impact from the use of these AI tools? If we're going to use them alone, we're going to be in this category, right? If we can use them and improve our worker efficiency, our worker overall wellness, we're going to be in this doubling category. And so I think that's where we want to be. And it's everywhere that we see now. You know, we're seeing AI in cars, driverless cars. We're seeing AI diagnosis, and we probably all have seen the benchmarks where they compare all the foundation models on their ability to diagnose medical errors or do the MCATs and things like that. We're seeing work with robotics, not being just programming a robot to do a task, but programming those robots to do tasks in conjunction with people, to the point where, people in the same area working on the same work product, part robot and part human. And then we're seeing, of course, throughout the business world, there's tons of AI work going on, and we're seeing lots of pickup of that. People have been deploying AI in a number of different places. Salesforce is one of those places who say they're saving $100 million annually by cutting 4,000 customer support staff, people at their work, and replacing them with AI systems. That's one of the things companies always want to do is reduce their costs, and this could be one way of doing it, but that's a big impact on people. And one of the things that we want to try to understand better is this really a good way to be doing that, or should maybe we be doing something else? Our Fed chair director has said one of the things that we are going to be looking for now is this different type of growth that we're going to see in industry, which is going to be jobless growth, because the growth is going to be driven by AI, right? And so the question is, if AI is producing all of this benefit for companies, is it really producing a better product, or are we satisficing? Is it good enough, or do we just not have a choice? And what we've seen from interviews and surveys with people is people have a lot of concern about having AI provide services for them. And I'm sure you've all done this too, is when you call up and you get the AI system answering the phone, and you go through your list of demographics, and they get all your identity, and then you ask your question, and then it says, oh, we can't handle that, we'll send you to somebody. And then you have to go through all that again. That's the number one frustration that people have with this AI and customer service. I think it's interesting that they have this empathetic concern in second place, which is AI is displacing people's jobs, and people feel uncomfortable about that. But I think the third one here is really one of the most interesting ones, is AI is going to provide the wrong answers. And I think we all have experience with that, of AI providing the wrong answers. And that's why so much of the research being done on AI transparency, AI explainability, and ethical guardrails around AI are so important, is because people have these worries, and they're very well founded, especially with generative AI. There's really nothing in the generative AI architecture that promotes returning truthful statements versus just returning things that look like they could be truthful statements. So anything that we do to get to a truthful statement is going to have to be outside of the AI architecture itself. So people have real problems with this. So the next question is, well, how well does AI work? And so this was a study done in 2023 looking at clinical diagnosis. And they did a number of trials, and they looked at how many times were the physicians superior to the AI, how many times was the AI superior to the physician, and how often were they equivalent, right? And I think we can see, this is a good example of one. Physicians are superior, quite a bit of the time. What is that, about maybe 28% of the time? AI is superior only about 10% of the time. But 45% of the time, they're very comparable. And so this kind of starts to beg the question of, how do we deploy an AI diagnosis system when this is the distribution of capabilities? There's a great paper that came out in Nature looking at just this idea of, well, a good idea is to combine these two. So we can combine the human and AI together and look about when they're going to be useful. And basically what this graph shows is, up here in the red, this is the number of studies where the human AI group underperforms either the best human or the best AI system. And in the bottom green, this is where the human AI group outperforms the best AI system or the best human system. And the things that they took from this study was, on average, the human AI combinations perform significantly worse. In performance losses in particular were highest in those tasks that involved making decisions, joint decision making. So the AI system and the person are trying to make a decision together, versus tasks where it was involved in creating content, like creating an image or writing text and things like that. And in those cases where AI outperformed humans alone, there were overall losses when we put them together. But where humans outperformed AI alone, there were gains in when we put them together. So a number of these things are dependent on the task and how we're combining them. And so that's really one of the things that we're interested in, because we can see that, computers are getting really, really good. And so we have Deep Blue for chess playing. We have AlphaGo for Go playing. But if you've ever seen hybrid chess or Cyclops chess, an average player paired with an average computer is capable of beating the most sophisticated supercomputer. And so we've seen this in a number of different tournaments and studies where, given the right combination of AI system and person and the right way to interact, we can perform remarkably better than either the person or the AI alone. So that's what we're really interested in, is how do we work with AI? And we've come up with kind of 3 things that are really important for us to be able to do this. The first is this notion of interdependence. How the AI team is structured together. Whoops. How they're structured, how the task of the AI and the person are combined together in order to achieve an overall goal. The second element is the structure of the team. How is the way they structured it? Is it hierarchical? Is it a flat team? Are there individual task groups that combine together? What is that structure? And then finally is the alignment between AI and the person. And so just to, for completeness here, this is there's lots of definitions of teams. This is our definition. Yeah, it's basically going to be multiple entities, so they could be AI or human, that engage in interdependent activity. So they must rely on each other to achieve the goals, while they perform their roles in a context-specific manner. So they can do very specific types of things. And we came up with these 3 kind of maxims, basically. The teams themselves are defined by their interdependence. It was there in the definition. It's the thing that connects people together. And if there's nothing that I'm vulnerable to you for, then we really aren't on a team. There's nothing, we're basically independent operators. Teams are effective by their structure. And so depending on the structure of the team, we can either increase the how smart the team is, how creative the team is, or we can increase how productive the team is. But we may or may not be able to do both. And finally, teams are trusted by their alignments. And so we'll kind of go through these things, and we'll start with interdependence. And so I'm going to run through a little thing real quick just to show you some of the kind of a graphical view of interdependence. And we basically break down the things that either the AI or the person does into this kind of graph, where basically there's a precondition, there's an input that comes from the agent, the task gets performed, and then there's a post condition that results, right? And so, this triangle will be lit up when this task is available to be run, and this triangle will be lit up when the task is completed. And whenever this is a task completed, this line tells you it's enabling the next task on the road, down the road. And all of these agents operate in this kind of OODA loop, the observe, orient, decide, act loop, where we're observing the system, we're orienting ourselves to the world in terms of deciding whether all the preconditions for our ability to take action exist. We decide on any kind of inputs to that action that we do, and then we finally take an act. And then that's going to change the world. And so if you look at a team here, we have 4 people on a team. The ultimate team goal is up here at the top, and there's 2 sub goals. And kind of the right side of the screen is working on sub-goal 2. The left side of the screen is working on sub-goal 1. But you can see they're kind of structured a little bit differently. So the preconditions for all of these are true, and so they will run, and the entities will run their task, and then the post conditions will be true. And in these cases, the post conditions fill in sub goals of this sub goal. This one connects with the preconditions for another entity. So these ones up here that have filled in the sub goals are called resource interdependence, because they're the only interdependence that we have between entities 1A and 1B are the resources that they're working on. And so if you think about a task where we're in a warehouse and the overall team goal is to move 50 boxes from the input area to the processing area, if we put more people into that group of people doing that task, it's going to be done faster. But if we leave only one person that task, he's going to have to move all 50 of them. So they're really interdependent on the number of resources they have to do. This other one is called required interdependence, and it's where the ability of entity 2B to work depends on the output of another entity. And so they're structured in this way, either by the resources that they're working with, or that they're dependent on the output of another. There's another type of interdependence where if an entity isn't working on their own goal, but helping another agent with their goal, we call it opportunistic interdependence. And so one of the things that these agents may do is say, this agent may say, oh, I found a box sitting on table A for you to pick up. And so now this agent doesn't have to do the search process. And so it provides some efficiency for agent 1A to go find that box and pick it up and move on. And so as we continue through this, they'll be filling up their sub-goals. You can see the right-hand side is taking a little bit longer because of this required interdependence. They have to take multiple steps. Both sub-goals are filled, and the ultimate goal is filled in there. So we have these different types of interdependence that are going to change different aspects of how the team are going to be able to work together. And in the literature, there's been a bunch of work on this under what's called the 3 C's. Cooperation, collaboration, and coordination. And one of the things that Claudio helped us with while we were down, while Kazu was finishing his PhD, was analyzing the literature and coming up with a consistent set of definitions for these types of things. And so basically coordination is when we have required interdependence. Collaboration is when we have resource independence. We have the same capabilities and it doesn't really matter which one of us does something. And cooperation is where we have opportunistic interdependence. And so this set of definitions gives us a way to talk about things consistently. And when we're analyzing results or reporting results, we can do it in a way that will be hopefully more, make the results more available to people or interpretable to people. So that's the interdependence. Our second thing is that teams are effective by structure. And so here's 2 types of teams. On the left-hand side, we have a person in their car. The car has an autopilot mode. Both the car is capable of driving and the person is capable of driving, and they're capable of doing it at the same time. So this would be, an example of a compositional collaboration system where the person and the car can collaborate. They're both capable of doing it, and they can do things at the same time. So if they do something at the same time, their inputs are going to be composed and somehow. On the right-hand side, we have an example of a coordination system where each kind of group of robots there has to wait until the previous robots finish their jobs on the car before they can start on their job. So when the very first car comes online, most of the robots are empty and they're not doing anything. And it's only when the pipeline gets filled does the entire group work. So what's the difference between these types of systems? Well, one of the things that you get when you add more robots to the production line is you get faster performance, but all the robots are doing their own thing, and they're not influenced by the other robots except for by how they work. And so the intelligence level isn't going to be better. With the left-hand side on the driverless car or the autopilot driving car, if the autopilot isn't capable of doing something or doesn't do something well, the person can jump in and do something. So we can actually increase the capabilities overall of the car driver, the autopilot driver system, by letting these guys interact with each other. And so the other thing that Kazu came up with in his dissertation was this notion of taking those 3 C's, but dividing them into this notion of, are we composing inputs or are we independent inputs? And if we're composing, that means we have the same action channel. There's only one action that's going to be taken, but that action, the input to that action is going to be some composition of the input from the AI and the input from the person. And so this can be something that's continuous, in which case we're running consistently, like in a car, or it can be discrete, like you would have in a chess match. And so we did a number of experiments. This was one of the experiments that we looked at, which was the Moonlander game. And we had a couple of different AI systems, a more capable and a less capable AI, helping the person navigate this spacecraft to one of the landing areas. And depending on the trial, the landing area would change. And we got some interesting results. When we looked at the high performance people working with the high capable agent, we saw a certain pattern of behaviors. And basically what they would do, the highest performance people would basically get the lander lined up and then let the AI land it. And so the way that they learned how to interact with the AI was getting everything lined up first, and then relying on the high performance capability of the agent to land the aircraft. When there was a less capable agent, the high performing teams knew that, oh, even at the end, I still have to make some corrections and go along. Whereas the low performing teams were interfering with the capabilities of the high performing agent, which was causing them to do worse. And they weren't doing enough with the low performing agent, which was causing them to do worse. And so this kind of drove the research into what are those things that we can do to make the things that the high performing people are doing more apparent, so that the low performing people it would be more natural for them to do that. And so the way we did that was in a second set of studies where we were looking at a combination of both the compositional and the non-compositional control. And so this case was an urban search and rescue experiment. If you can see here, we've got 3 little robots running around, labeled with the numbers here. And the robots can have obstacles in their road. There can be, and they're looking for different survivors of this natural disaster thing. And the way that we structured this program was we could do it in two ways. We could have basically this compositional control where the person could jump into any one of the robots and help them when they needed it, or we had the robots just operating on their own. In this case, we did 4 different kind of user interface tweaks to be able to see, can we push people to push lower performing teams to the higher level performance through these different user interface interventions. And you can see from the data here that no, none of those work. They were all pretty much the same. But the interesting thing was they were all better than the AI alone. So regardless of what we were doing, and what the data shows is we were basically doing about the same thing with all these different interface elements. The human AI combination was always significantly better than the AI combination alone. And so that was a really important piece of data for us. And that led us to look at one of the characteristics of how good teams work together. This image in the lower left here comes from Sandy Pentland's work on building great teams. And what he was able to do is just by tracking the proximity of people with each other and a few other variables with that. Predict how well that team would perform. And this graph kind of shows you have this parabola here where you have really good team performance. Of course, the best team performance up here, and as you come down, but you have these areas that are bad performance. And so we've always been kind of looking for this parabola. And one of the things that we found here was, if we were to look at how the team handled opportunistic interdependence, where the AI is going to help the person do their task, or the person is going to help the AI do their task, just by saying, hey, I saw something that you're interested in. Oh, I knew you needed a box to be moved, so I moved that for you. Whenever if you look at the number of cases where those opportunities were never taken, the performance was low. If you look at the opportunity when they're always taken, the performance is low. And then there's a middle ground where we see this parabola. And so this is another great example that I think there's going to be this kind of there's going to be this sweet spot where we want to ensure that we're doing enough for others, but we're not doing too much. And I think when we think of good teams, that's often the case, that's often true. We need to be helping others do their task in order for us to get more done as a team, but we can't do too much. We can't do their job for them. And so that was a great piece of data for us. So what are those things that we're doing to build these effective habits? They're about independence and structure. The key questions that we're working on now is, how do we leverage these AI capabilities to amplify human capabilities? And how can people amplify the AI capabilities? So we're looking at for it to be this bidirectional street. And so again, if we're thinking about recommender systems, these are things that are discrete compositional control. So you think about on the right-hand side here. So on the left-hand side, we have our icons for the driverless cars. We have both the robot and the person controlling the steering wheel, and that controls the car output. If the person doesn't put any input in continuous compositional control, no input is an input. It means the person wants to keep going straight, but if the robot wants to turn, those two things are averaged and the car ends up turning. In discrete compositional control, it's something like you would use with a recommender system in something like playing chess. And so the person thinks about the move they want to make. They go to a computer program, or often multiple computer programs, get the computer suggestion for the move. They think about it, they negotiate it, they may do some new strategies with the computer, and then they choose their answer, and then they make their move. So here we go through this reasoning process. And it's that reasoning process that I think is one of the interesting things now about how we're going to be able to use AI systems to increase the performance of teams. And a big part of this is going to be the trust that people have in the AI systems. And so in one of our maxims here is teams are trusted by alignment. If we can show alignment between the things that the AI are optimizing for and the things that the person is optimizing for, if those two things are aligned, things are going to be predictable and trustable. If they're not aligned, then you're going to get surprises, which is generally not going to be something that that is going to be interesting for people. So we have three different questions with alignment. First is, how can AI learn what people want? So what is the procedure in which we either tell AI what people want or have it learn? If we're having it learn, is AI learning the right thing? Or is it actually implementing the thing that people want, or is it implementing something different? And then finally, how should these two things adapt to each other as we see new and novel environments, so that they behave, again, predictably, and that the people can rely on the AI output. So this is an example of a system that we're developing that's just going into experimentation right now, that's looking at the first two of these issues of how can the AI learn what people want, and then how can they represent that effectively? And so here we go through a little process where we ask people to basically do trolley problems, right? To do ethical reasoning problems. And so in this case, there's a hospital emergency. Should they prioritize treating many patients with moderate injuries or focus on fewer patients with severe injuries, right? And depending on what you're doing, we're trying to categorize what type of moral reasoning you're doing. And so once you select this, focus on severe cases, it offers you an analog problem, right? Which is, if you're developing a new medication, would you also prioritize the rare events or prioritize the larger number of more moderate events? And this is a case where people will often change their answer here, right? But in doing that, we're starting to collect how people are reasoning through, in this case, kind of moral type decision problems. And so with that, we can kind of create a model of the reasoning, the things that people value in their reasoning, and we can put them into a natural disaster situation here. In this case, it's a wildfire crisis. And we have this scenario where a wildfire is approaching a town with 2,000 residents. We have to make a decision. And the AI has come up with a couple of answers that are applicable. The person can come up with their own answer. And they also have this button up here where you can click on, well, what are some more alternatives, right? And so here you can see that we can prioritize safety, and 3 out of 5 expert AI agents recommend this one. Or we can minimize harm, which is the non-malevolence approach, and 3 out of 5 experts recommend that one. So if we go look at the alternatives, we can see here are some other ones some other kind of ethical strategies that we could use for making this decision. And the purpose behind all of these are to explore the decision, look at the justification of what is going to be the impact of that decision in terms of things like safety, sustainability, fairness, and so on. And engage the person in thinking about the problem a little bit more deeply so that they can make the best answer possible. Once they make their selection, they're kind of given one final summary with some explanation about things and what are the key impacts, what are the key drawbacks of this, and then they can make their final, and then they go on. And this is all part of kind of a methodology around human AI interaction developed by a researcher at Harvard, Zana, I forgot her last name, called cognitive forcing functions. And one of the big things that we want to do is to make sure that when people are working with an AI system, and especially as the AI system is working well, they're not just accepting answers and like hitting next when you install a program, right? They're actually thinking about it. They're actually exercising their own decision-making capability. And this is going to be one of the areas where I think to really look at the capabilities of making human AI systems better than humans alone or AI systems alone. One of the biggest capabilities that we need to be able to do is to make sure that this interaction with AI is beneficial to the human, because that's the point where we're going to be thinking more out of the box. We're going to be looking at the entire search space and coming up with those, engaging the person in a way that will hopefully increase their skills and keep their interest in making these decisions. So unfortunately, I don't have any results for this yet. This is just going into experimentation, like in the next 2 weeks. And so actually, I'll I'll ask Claudia to send out the URL for the experiment. So I hope you can all take it and experience it, and we can kind of improve these systems together. So there's a few other things that we're looking at too. One is this notion of how do we detect and mitigate groupthink. And groupthink is when you have some sort of pressure that against your better judgment, you're going along with the recommendations of the group. And one of the things that you saw in that example there was 3 out of the 5 experts think this is the way to go, right? And so one strategy for not thinking and kind of deflecting responsibility would just be to pick the ones that most experts think, pick the solution that most experts think would be the one that works. And in particular for AI systems where you may not know what they're valuing, what they're optimizing for, that can be a real problem. And so one of our PhD students is looking at this notion of groupthink, and again through a slightly different way of doing this cognitive forcing function, where we're having the person look at implications of the performance effect of stating what they really believe versus going along with the group. One of the other projects that we're doing that kind of cross-cuts a lot of the work that we're doing is looking at how do we have an unobtrusive measure of trust. If you look at the AI trust literature, most all of the measures of trust are going to be survey-based. And so that's intrusive. It's after the fact, and it kind of rolls up a number of different things into this notion of trust. Is it reputational trust? You heard that the AI agent was good, and so you trust it. Is it experiential trust? You use it 50 times. It seems like it works, so you trust it. And so we're looking for some unobtrusive measures for that. And typically what you see in the literature, if we do have an unobtrusive measure, it's going to be a correlated measure. And so people have looked at things like, have you used it? Do you end up using it? Have you used it a lot? How reliable is it? That has been one of the measures of it. And so the notion is, if you used it, then you must have trusted it. And of course, we know that's not true. I used it because I was too busy doing something else, and it was better than doing nothing. And so we're looking at this notion of prediction as being an unobtrusive measure in trust. And so as part of our cognitive forcing function, we're looking at predicting what outcomes might be. And if the outcomes appear in that group, then you're getting how the AI systems are working. And so you're much better able to, we're much better able to think about you trusting them. And so we're doing some experiments looking at the correlation between prediction ability and survey-based trust. And like I said, a big part of our work around these cognitive forcing functions is looking at things that make the tasks that were given to the user engaging and challenging, so that their satisfaction with the job, with the satisfaction with the work that they're doing, actually increases. There's a number of different cognitive forcing functions that are really onerous, that are things like you ask the AI system for its recommendation, and it'll delay 30 seconds before it gives it to you, because you're supposed to reflect during that time, right? But the only way that they encourage that reflection is just by delay, which turns out to be really frustrating, and not surprisingly, people really dislike that. And so we're looking for ways that are going to engage and actually, stretch the person's abilities while they're doing that. And so there's a line of research going on that. And then finally, we're looking at biomeasurements of participant engagement. So as the recommendation systems are making their recommendations and you're negotiating as part of your final answer, how engaged are you in that process? And so we're using EEG and some measures of blink rate and blink rate variability to look at participant engagement, in order to make sure that when we're collecting this data and we're looking at the characteristics of the human AI team, are things not going well because, you know, typically we're running these experiments on undergraduate students who are doing the experiments for class credit. And so are they doing it because they're just checking out and hitting next, next, next? And so we're wanting to see, is that happening in our experiments? And then is there a way that we can actually deploy this so we can see, you know, this person's really capable, but he's on hour 11 of a 12-hour shift and they're just tired. They shouldn't be making a decision. They're just too tired to do it. And so we're hoping that's going to increase our ability to use these recommender systems to create joint human AI decision-making in a much more effective way. And so just leave you with these three maxims to kind of spark your thought a bit. You know, teams are defined by their interdependence with each other. They're made effective by the way that we structure them, and we trust them by the way that they're aligned. And all three of these are very important things. And until we get all of them, I think we're going to be not using AI to its fullest potential. Thank you.
Thank you, Professor Eskridge. Now we have some questions to you. What happened? Tom.
Ele caiu.
Ah, ok.
Ele tem que voltar.
Ok. Let's try. É interessante salientar, que deixar registrado aqui, está voltando. Sorry. So, here, okay. Everybody works with technology, and everybody has a problem with technology.
That's right. This was one of those examples of just hitting the red button because it was stop share, and it wasn't. It was exit. So.
Okay, no problem. The first question to you.
Yeah. Can a team work even if some parts of the team don't collaborate? Again, the effectiveness is going to be part of that structure. And so depending on the structure you have, collaboration can be necessary or not, right? And when in our definition of collaboration, it's the agents have the same capabilities. And so what it's going to mean is that if they are collaborating, you're going to get the job done faster. But if you have for example, two robots moving boxes in a warehouse, if one robot doesn't do anything, then it takes the other robot twice the amount of time. And then is there a minimum number of entities that must be engaged? It, again, depends on if there's any constraint on the goal. If the goal is just accomplish moving 50 boxes, then you would need one. And one would be able to do it, but it may take that one 24 hours to do it. If you have to move these boxes in a particular amount of time, then yeah, you have to have enough of those members working collaboratively in order to make that time goal. Yes, human traits definitely interfere with human AI interaction. Personality types. There's a whole bunch of work, especially in the trust literature, on propensity to trust and propensity to distrust. And so the attitudes that people come into working with an AI system without ever having seen it before really play a big role. And so that's one of the key parts about alignment, is that if we can show the user that the things that the AI system is optimizing for matches the values, the things that the person thinks it should be optimizing for, they connect much quicker. But yeah, there's a lot of literature on especially propensity to trust that has affected AI interaction. Oh yeah. And policies, yep. Yes, and again, this is another part of alignment. And actually, we've been doing work on ontological alignment as well, which is, when I was talking about can AI learn what people value, but then can the AI represent that properly? That's where this ontological alignment comes in, and the whole area is a big open problem right now. What we've done in past systems, looking at ontological alignment between agents that we've developed and agents that other people have developed, has been to learn translation based on effects. And so if we give it a goal and agent 1 does something and agent 2 does something else, then we can start to infer that was done to accomplish that goal, and so this is what they must be meaning. And so we've done previous work on agent systems in cyber defense that have done that. And there's a couple of papers on SOD and MIRA that are out there that talk about that.
Oh, thank you.
Yeah.
So thank you very much. And thank you again for your contribution. The colloquium is not only about archives and technologies that can contribute to archival science, but it's about the interaction between humans and disruptive technologies, basically. So thank you very much.
Yeah, very well. Thank you for having me. It's been great.
Now I will talk a little in Portuguese. Sorry.
Sure.
Então, novamente eu gostaria de agradecer ao professor Tom pela contribuição, agradecer a audiência. Nós estamos gravando, né? Obviamente isso vai ficar registrado e disponível no YouTube. Vocês devem ter percebido que várias vezes eu olhei para cima, porque eu estou com 2 computadores, mais o celular aqui, né, acompanhando tudo, e mesmo assim, né, ficou comprovado, todos aqui são especialistas em tecnologia, e mesmo assim nós tivemos alguns problemas. Mas, novamente, eu agradeço a todos, eu agradeço aos membros do meu grupo, o R.E.G.I.I.M.E.N.T.O, o grupo de pesquisa, agradeço aos amigos palestrantes, e desejo a todos uma ótima sexta-feira e um excelente fim de semana. Muito obrigado. So, thank you again, Tom, and have a nice last weekend and a nice Friday night. Thank you. Thank you very much.
Thank you.
Bye-bye.
Bye.